Bismillahirrahmanirrahim. I am Dr. Abdalrahim Pharmacognosy Department to give presentation or lectures for third year students. The title of the lecture is Spectroscopic Applications to Structural Elucidation of Natural Products. Before proceeding to apply spectral data to a natural product, we should have pure compounds. These pure compounds can be obtained by chromatography and related techniques. The first step towards identification of a natural product is to measure physical constants, which include melting point, refractive index, and optical rotation. Melting point is determined for crystalline compounds, not for amorphous ones. And its value actually indicates purity. Crystalline compounds are marked by having sharp melting point. Several methods exist for melting point determination, including the sulfuric acid or silicon oil bath, the older method. More recent methods include hot stage microscope or Kofler microscope. Third method, more recent, electronic automated apparatus. The value obtained from these machines is called uncorrected melting points. If there are any impurities in the sample, they tend to lower the melting point. To confirm the identity, we make mixed melting point or determine the melting point of a mixture of our sample and the reference sample. It should not be lowered in this case. The second constant is optical rotation, determined for optically active compounds which have chiral centers or chiral carbons. Most natural products actually are formed by enzyme reactions, and therefore they are usually optically active. First, we prepare solution of known concentration of natural product in a known volume of optically inactive solvents such as nisolone or colloidal. The optical rotation obtained by this way from the machine is called polarimeter. It's called observed rotation. It is not constant. The constant is the specific rotation. It can be obtained from the observed rotation by using the following relationship. Alpha D25 equals the observed rotation which we obtain from the machine multiplied by 100 over the concentration of the sample in grams per 100 ml multiplied by the length of the sample tube in decimeter. D means sodium D-light, determined at certain wavelengths, which is 589 nanometers. 25 means that we measure the rotation at 25 degrees centigrade. The observed rotation is affected by the nature of the compound, the sample concentration, the length of the sample tube. However, the specific rotation for a particular compound should be constant. It has a physical constant and helps in identification of optically active compounds. Natural products may have one or more chiral center. Hesperine, for example, has one chiral center. Isoleucine has two chiral centers. Quercetin is optically inactive. In case of optically inactive solvent, we such as quercetin here or a camphor, there is no optical rotation, but it is determined for combustible aspartame, which has a chiral carbon, and isoleucine, which has 2 chiral carbons. The third constant is the refractive index. It is determined for liquids. It is constant for pure neat liquid. In solution, the value of the refractive index depends on concentration. As you know, refractive index is equal to the sine of angle of incidence or the sine of angle of refraction. However, most important natural products are solids. The second step in identification of a natural product is determination of the molecular form. It can be determined by use of 2 methods. First method is elemental analysis, combustion analysis, or by the use of high resolution mass spec. The more accessible method is the use of elemental analysis. However, it needs highly pure sample. In the elemental analysis procedure or combustion analysis, we first make a qualitative elemental analysis by the use of the sodium fusion test. This method detects the presence of nitrogen, halogens, and sulfur in the compound. Carbon and hydrogen are imperative to be present in any organic compound, and oxygen has no qualitative test. The second step is the determination of the quantitative, or to perform a quantitative elemental analysis or combustion analysis. In this step, we take known amount of the sample and make ignition and measure the amount of oxides formed. From the amount of oxides, you can obtain the percentage of each nucleus or each atom in the molecule. For example, atom A equals percentage of element A from combustion analysis data multiplied by the molecular weight of the compound and divided by 100 multiplied by atomic weight of A. Okay? If in many cases the molecular weight may not be known, and we resort to the determination of sub-ratio or combustion ratio for each element or each atom. For example, sub-ratio of carbon, the percentage of carbon over 100 by 12. In this case, we do not multiply by the molecular weight. The same is repeated for hydrogen and for the nitrogen. For oxygen sub-ratio, we subtract the percentages of our atoms from 100 and divide the product by 100 multiplied by 16, which is the atomic weight of oxygen. In this way, we can obtain what's called combustion ratio. Each element has a fraction called sub-ratio for that element. If you know the molecular weight, then multiplication of this sub-ratio by the molecular weight produces the exact formula of the compound. If you don't have our access to the molecular weight, we can determine the empirical form. For example, combustion analysis of a compound produces following combustion data: carbon 62.6, hydrogen 11.4, and nitrogen 12.3. Subratio can be calculated, as we said before, for carbon, hydrogen, and nitrogen, and oxygen. Okay? Dividing by the lowest subratio, we can obtain the empirical formula. خلاص, empirical formula. The exact formula can be obtained if you know the molecular weight, which can be derived from mass spectrum of the compound. The highest peak in the mass spec, which has the highest M/E value, can be presumed to be the molecular ion peak or the molecular weight. Multiplication of the combustion subratio by the molecular weight produces also the exact formula, as you can see. Therefore, the exact formula is the same for this compound like the empirical formula. The exact formula can be the same or multiple of empirical formula. However, the molecular ion or the molecular ion peak of the sample should meet the criterion for the molecular ion can be used to explain the formation of important high mass fragments. Knowing the exact formula, we can determine the unsaturation or index of hydrogen deficiency of the compound, number of rings or double bonds. For example, benzene has unsaturation of 4, because it has 1 ring and 3 bonds. However, this value should be derived from the exact, not the empirical form. It can be obtained from the following relationship: the number of tetravalent atoms in the molecule minus half the number of monovalent plus half the number of trivalent plus 1. The molecular formula can be also obtained from high-resolution mass spectroscopy. The exact mass of a compound, exact mass, is not integer. It has a decimal because the exact atomic weight is not integer, except in case of carbon. Nitrogen, for example, has an exact mass of 14.00307, hydrogen 1.07825, oxygen 15.9949 atomic mass units. Therefore, molecular weight, exact molecular weight, is or has a decimal. Comparing this exact molecular weight to a combination of data known as binary tables, you can obtain the formula of the compound. Formula, the exact, the observed exact molecular weight should not differ from the molecular formula by more than 0.003 atomic mass units. This can be used to determine the formula of the molecular ion and also the fragment ions. This technique, mass spectroscopy, is called high-resolution mass spectroscopy technique, which uses two mass analyzers. Mass spectroscopy, طبعا since we use mass spec in obtaining molecular formula, start by use of explaining the use of mass spectroscopy and determination of the structure of natural product. Mass spectroscopy uses to determine the structure and the molecular weight formula of a natural mold. The low resolution mass spec can be used to determine the molecular weight, whereas the high resolution mass spec can be applied to determine the molecular formula. Mass spec is determined on one basic principle. It's always possible to determine the mass of an ion in gas phase. Mass spectrometer usually performs three major functions. First function is the bombardment of the molecule in gas phase with high energy electrons. Second function is the acceleration of the ions. Third function is the detection of the ions. The first step is the bombardment. The molecules and gas phase are bombarded with high energy electrons. This will result in electron ejection and formation of positive ions. This is the main event. A less frequent event is the electron capture. That is a very, very minor event. This technique for ion generation is called electron impact or electron ionization. And we can here observe the formation of positive ions. طبعا the spectrum which results from this process can record the positive ions formed, not the fragments or negative ions. This is a sketch for how the mass spectrometer performs the functions, the three functions. First function is some molecules are admitted into ionization chamber, which is maintained under high temperature and high pressure. It is present here in the form of a gas form. The high energy electrons will bombard these gas molecules and they make what is known as electron ejection. The positive formed ions are accelerated under high voltage into magnetic field, which is called analyzer, and separated according to their mass over charge ratio, and ultimately strike the detector system, and a mass spectrum can be obtained. Mass spectrum, as you know, is the diagram which makes a relationship between the mass over charge ratio versus the relative abundance. It shows some peaks here, base peak which has 100% abundance and the nuclear peak which has the highest mass. This peak should possess the value of the molecular weight, and it is an odd electron ion. After ion generation, the ions, as you can see, as you saw in this diagram or the sketch, are accelerated into the mass analyzer in presence of negative potential, and separated in the mass analyzer according to the mass over charge ratio. Okay. For generation of a molecular ion, only high energy of electrons should be about 15 electron volts. Energy more than 15 would lead to fragmentation of the molecular ion. Process of fragmentation is also important because it can be used to determine the structure of the compound. Therefore, in most instances, we use electrons with 70 electron volt, an energy of 70 electron volt. Mass analyzer, as you saw, the region where ions are separated according to the mass over charge. It is here a magnetic field. In presence of a magnetic field, charged particles describe a curved path. A curved path. A curved path. Okay, as you see, the radius of this path is can be determined or directly proportional to the mass over charge ratio. M على Z ratio equals H square multiplied by R square over 2V. Mass over charge هنا M على E equals the mass because the E is unity 1. It's equal to the mass equals H square, extensor magnetic field, multiplied by R square, the radius of the ion mass, and divided by the V, which is the potential of accelerating units. The larger the M value, the larger the radius of the curved band. This technique for ion generation is called single focusing because the analyzer consists only of a magnetic field. However, you can use double focusing system which provides the high resolution data, as we saw in determination of the molecular form. Application of mass spectroscopy. First, determination of the molecular weight and molecular formula. As we said before, the low resolution data provides the molecular weight, whereas the high resolution data provides the molecular formula. The stability of the molecular ion sometimes is unstable. Stability and its abundance actually decreases in the following order. Aromatic compounds usually the highest stability, followed by conjugated alkenes, followed by various sulfides, and the shape in this sequence. For example, alcohols have low stability because they undergo dehydration, and molecular ion cannot be seen. In this case, we resort to the use of mild ion generation techniques. Nitrogen rule, probably you heard about this term before, states that the molecular weight of a compound should be even unless it contains odd number nitrogen. This is the first step, the molecular weight and molecular formula. Second, value of mass spectrometry in the fragmentation process. It gives an idea about the structure, because each chemical structure has a certain way for fragmentation. Includes 2 bond and 1 bond cleavages. One bond cleavage usually produces odd electron radical and even electron ion. Our molecular ion is odd electron ion. Upon one bond cleavage, whether homolytic or heterolytic, provides a even electron ion and odd electron radical. A dot, this point means radical, odd. No dots, no points means it's an even electron. 2 bond cleavage of a molecular ion produces a neutral molecule and odd electron ion. Neutral molecule and odd electron, as you can see in this example. We can briefly describe what happens to the molecular ion in this sketch. This strong and odd electron molecular ion undergoes One bond cleavage produces even electron ion and radical. Two bond cleavage produces odd ion and a molecule. Bond cleavage or nuclear ion can be one bond or two bond, can be homolytic or heterolytic fission. Homolytic fission of one bond produces a radical and even electron ion. The same for heterolytic fission. Produces also ion and other electron ion and a even electron ion and a radical. However, in case of homolytic fission, each fragment acquires one electron on the one, whereas the heterolytic fission, one fragment acquires the two electrons, but the result is that we have even electron ion and odd electron radical. Mass spectrometer observes only the positive ions. Elimination, the type of cleavage of nuclear ion, it involves two bond cleavage where the hydrogen goes to uncharged fragment. Rearrangement is also a two electron or two bond cleavage, but the hydrogen goes to the charged species or charged fragment. In both cases, elimination and rearrangement, a neutral molecule and other electron ion is produced. Here we summarize the factors which influence the formation of the fragments or fragment abundance. Fragment abundance, if the abundance is high, means the fragment is stable. The first factor which influences the abundance and stability of the fragment is stability of production by electron sharing and delocalization of electrons. For example, amine type species can be stabilized by delocalization of electrons to form this structure. This confers stability on such type of ions, of fragment ions. Stability by resonance also observed for aromatic compounds, which have the potential of forming benzylic cation, because benzylic cation is stabilized by a resonance and formation on average structure called tropolonium cation. The second factor which influences the formation of fragment ions is large group preferential loss. For example, in this case, we have this tertiary carbonium ion or nuclear ion. The potential of loss of tertiary butyl is more strong than the loss of ethyl or methyl, because this bulky radical tends to make stability more than the ethyl and the methyl, with that for a tertiary radical. خلاص. فعشان the Stephenson's rule isn't specified that large groups are preferential loss. Potential of losing tertiary radical more than the ethyl, more than the methyl. Cleavage occurs at the branch points, because this is the weak point of the molecule, which produces more substituted carbonium ion, than more stable. Cleavage of and production of primary ions is not favored at all. Processes in which fragmentation proceeds the formation of neutral molecule are favored, because these neutral molecules are stable. such as the loss of carbon monoxide, dioxide, water, HCl, ethanol. The loss of these molecules is favored and occurs by two-bond cleavage. Stevens' rule, the homolytic characteristic of a fragment ion depends on the electron potential of the fragments. For example, if P has electron potential higher than A, it will acquire the two electrons and the electrolytic fission occurs. If A has higher electron potential, it will acquire only one electron because it does not have a charge. And also, that's the same result obtained, but we have here homolytic fission. Electron potential, according to this rule, influence whether homolytic or electrolytic fission will take place. Factors influencing the fragmentation process. There are three outlines or factors which influence fragmentation process. First, the weak bonds are preferentially broken. Stable fragments, not only ions, are favored to be formed. In some instances, fragmentation process depend on the ability of the molecules to assume cyclic transition states, and we will talk about McLafferty arrangement later on. Examples of common fragmentation: cleavage of aliphatic carbon skeleton usually occurs at the branch points because it produces no substituted carbonyl. Cleavage of compounds containing heteroatoms or double bonds or aromatic ring occurs beta with the heteroatom, double bond, and aromatic ring because it produces stable delocalized carbonyl. Cleavage of carbonyl occurs alpha to the carbonyl because it produces stable psyllium cation. Cleavage may also occur alpha to a carbonyl, to a heteroatom, alpha to a heteroatom. الهيترواتوم ممكن two possibilities, beta heteroatom or alpha to the heteroatom. We can discuss this. First, we have the branched hydrocarbon. Occurs طبعا عملية الكليفج occurs at the branch point, and we can either lose from the molecular ion. We can lose this is the molecular ion after ejection of one electron. We can lose a methyl radical, okay, and formation of this tertiary carbocation, or lose n-propyl radical and obtain tertiary butyl cation. طبعا as we said before, large groups are preferential loss, وبالتالي the process in which this cation is formed more favored than here. Both of them can be observed, but this will have higher abundance than this one, because large groups are preferential loss according to the rule we explained before. Cleavage occurs also before beta to a heteroatom. The formation of nuclear ion from compounds containing heteroatom X, O, N, or S, or argon occurs by ejection of one electron from the lone pair. Then beta cleavage will form resonance stabilized carbocation plus this radical. The more also this radical is substituted, the more this process is favored. Here we have ether, for example, ether. This molecular ion cleavage occurs beta through the heteroatom, and this ion is formed because it is stabilized by delocalization of electrons. Cleavage also occurs beta through the double bond. The double bond containing compounds tend to form ion by loss of one of the pi electrons. Formation of this molecular ion. Cleavage occurs beta through the double bond formation and the formation of resonance stabilized allylic cation is observed. Also radical here is tertiary radical also favors this process. In case of aromatic ring, also cleavage occurs beta to the heteroatom, beta to the aromatic ring because the formation of benzylic cation, which is stabilized by resonance as we said before. In case of carbonyl compounds, cleavage occurs alpha to the carbonyl. First of all, the formation of nuclear ion occurs by loss of one of the well-known pair of electrons on oxygen, and then alpha cleavage occurs with the formation of a psyllium cation. Psyllium cation is resonance stabilized. بالتالي its abundance will be high, and it can be easily observed. Cleavage may occur also alpha to a heteroatom. In this case, heterolytic fission will occur of the bond connecting oxygen and carbon with the formation of substituted carbocation and O radical. Cyclohexene, for example, which is cycle compound containing a single bond, undergoes retrodisorder fragmentation, cyclic fragmentation, with formation of butadiene and ethylene cation. This two-bond cleavage produces a neutral molecule and or the electron ion, either ethylene plus butadienyl cation or butadiene plus ethylene cation. Well, that can be observed in case, for example, it's called C ring, undergoes retrodisorder fragmentation. Another also non-fragmentation of nuclear ion is known as McLafferty rearrangement. This rearrangement occurs when the molecular ion can assume appropriate 6-member cyclic transition state. This rearrangement involves the migration or transfer of a gamma hydrogen atom to an oxygen, and observed with some compounds such as ketones, acids, and esters. In case of ketones, gamma hydrogen transfer occurs, and there is two-bond cleavage of this bond between carbon and hydrogen, and the carbon-carbon bond results in formation of an olefin and an odd electron ion, which is stabilized by resonance. In case of primary carboxylic acid, with alpha carbon not substituted by alkyl groups, we have a characteristic fragment ion at M-Z 16. In case of esters, there are two ways for fragmentation, either of the alkyl group, in which gamma hydrogen transfer also produces the same results, or in the ester parts, or the alkoxy group, Also here we should have a gamma hydrogen, but for to obtain a gamma hydrogen, we should have at least 2 carbon alkyl group. Both fragmentations are observed in the mass spectrum of esters. If the ester can or has a gamma hydrogen present. These are some of the most important fragmentations or common fragmentation pathways observed in electron ionization mass spec. In some instances, the nuclear ion may be not observed, and in this case, we can use mild ion generation techniques to observe or to determine the molecular ion. Examples of these ion generation techniques involve the chemical ionization mass spectroscopy, which uses reagent much in high excess of methane, ammonia, or isobutane. This is used for the compounds which are labile natural products. We observe here quasi-molecular ion or pseudo-molecular ion, which is not exactly molecular ion plus hydrogen or cation, or not exactly molecular ion. Okay, for example, in using methane, we observe pseudo-molecular ions at MO plus 1 or MO plus 29 ethyl or MO minus 1 plus. Using ammonia as a reagent gas, we can observe MO plus 1 or MO plus 18, which corresponds to M plus ammonia. The second mild ion generation technique is the fast atom bombardment mass spectroscopy, FAB mass. One of the common mild ion generation technique which uses xenon or argon of high translation energy to achieve or carry out the process of ion generation. Here, this technique is used for non-volatile compounds or large molecular weight compounds. Solid molecular ions that may be observed here, MO plus H or MO plus sodium or MO plus potassium, and the positive mode. The third ion generation technique is electrospray ionization mass spec, ESI, MS, which uses high voltage across impolized needle and usually fit at the end of at the outlet of an HPLC. Used for polar natural products and produces in the positive mode MO plus H and MO plus cation plus, and in the positive mode, and in the negative mode you have MO minus H minus and MO plus amine minus. Another ion generation technique is the matrix assisted laser desorption ionization or MALDI. This technique uses laser beam or nitrogen UV laser used for determination of the molecular weight and peptide sequencing of very high molecular weight compounds such as proteins. Here we observe the formation